Okay, so I guess the last topic for today would be the polynomial regressions, right here. Okay, actually polynomial regression is pretty simple in a way that you already know the model. So the model is actually not polynomial. The model is still linear regressions, but all you do is you just transform your x into multiple x's. Okay, for example, think about this. If I were to think about this is x1, right? This can be my x2. This can be my x3. If you think about it like this, right? Your model become y equal w0 plus w1 x1 plus w2 x2 plus w3 x3. Okay? This one is actually just multiple linear regressions. Right? If you don't think about x squared and x to the x cubed, you just think about x squared is just another x cubed is another x, then this is just multiple linear regressions, which you already did just previously. So I guess polynomial regression is just a way to I guess in a way that we do it, implement it in here. We just have to construct new x's. That's all, and plugging everything into the multiple linear regression model. Okay, and I will show you how to do it. It's pretty. There's a tool that helps you do that already, so that's pretty convenient. Okay, so we're going to go through another one called polynomials. So this one, right? Okay, so let's do the C1 first. Okay, C1, not OINB. Okay, so I'm going to go through the same thing very quickly. So importing the wait, where is it? Nope, I want this one. Okay, so importing the utility function, same thing. Go through that quickly. And then I'm going to go to loading the library. So this one is again, as I mentioned, it's just another type of linear regression, multiple linear regressions. So I'm just loading the linear regression definition from the scikit-learn. But the thing that are different is here. So I'm downloading something called polynomial features. So feature is x. Okay, so I'm going to create the features by from polynomial functions. And as you can see that this one is actually not the model. This one is called from the processing module. So when you do all the x's, that's your data processing part steps. But then when you're building the model, it's still linear regressions as usual. Okay, let me show you this, how to do this. There's actually quite, the tool is pretty nice to use actually. So let me show you. Okay, I'm going to run. So this one's the same thing. I'm loading the data, extracting data, and then splitting the data. Okay. The thing that I want to set first is actually, I want to do parameters equal to 3. So I want to do up until x cubed. So that's what the parameter is for. Okay. Okay. And what I want to do is that I want to generate my x up to the third degree. The way that I do, I call this polynomial features, and then I input, like for example, degree equal to 3, for example. Okay. So this one will generate up to, I think it's x cubed. We'll see. It's either x cubed or x squared. I don't remember, but you set the degree, right? Again, you can hard code it like this, but I'm going to show you in the other notebook that I can automate this process. So I want to make sure that I can do it like automatically. So I want to do something like this instead. Params. It's the same thing. Okay. So when I do like this, then I can declare all the parameter I want beforehand, and then I can inject it in here in the other code. So that's why I put it in here for you to see. Okay. This one is going to be named poly. Okay. And then I can do something like this. I can do poly dot transform, fit and transform. Okay. And then I can do X train. Check that one out. Okay, so I guess the polynomials to the third degree is squared. Actually, it's square. Okay, so what you see is actually the x to the actually when you are doing the third degree, you are doing something like this. Okay, it's gonna be w0 times x to the 0 plus w1 x1 plus w2 x2 plus w3 x3. I think that's what it's doing. So there should be 4 columns in here, right? So the first column is always going to be 1, right? Because x to the 0 is always 1. Hence the ones in here. Like this one, like this is x to the 0, so the 0th degree, right? And then x to the first degree, the power of 1, so this is the original value of x, right? And this one is x squared, and this one is x cubed. Okay, so that's what it is. That's why there are 4 columns, because there's additional 0th degree polynomials on the first column. Okay. Okay, so here I show you that the value actually makes sense. Let me just show you this one. Okay, I want to inspect the value to make sure that it's actually makes sense to when we think about it mathematically. So wait. Okay, I have to do x train poly and x test poly. Okay, so hold on. I have to do this one. There you go. Okay. So what you are seeing here is that this one is the original data. It's 34, 7.73. That's original XL stat, essentially, right? So notice that this 34.41 comes into the second column, which is the x to the 1 power, right? But you already have the x to the 0th power, which is 1, always going to be 1. This one is squared. This one is cubed. So you can kind of verifying the data from here. That's just to make sure that it makes sense, okay? But then once you already have this, then you're done, right? Because you already have your data. The rest is the same, which is to creating the model, fitting the data, and do all these evaluations, okay? So let me just go through them rather quickly. Okay, so first I want to instantiate the linear regressions model like that, okay? And then I can do this one, fitting. Okay, and then I can do predictions and prediction, yeah. And then I can do the testing, everything, right? Let me just show you real quick. Okay, there you go. Okay, so as you can imagine that even though we're doing the linear regressions, but our columns is actually polynomials generated, right? So now you already have the curve data, right? Which, as you can imagine, that this one should fit your data more better, right? As you can see from the residual, right? I think my residual should look better. Like you do have some outliers in here, but in general, it does have less, like a more random errors. And then your R square, let's check out your R square, okay? So your R square is already 0.61, right? I think from my recollection, for simple linear regression, you have 0.5. So you do have a better fit when you do polynomials, okay? And then, this one is the degree of 3. So, we don't have to stop at degree 3, right? We can also increase your degree into the 4th order polynomials. For example, I can change my degree into 4. You can try that, right? And then rerun the whole thing. So it does change a bit, right? Because when you have more degree polynomials, then your curve start to get more, I guess, more wiggles. You can change the nonlinearity in your curves, right? Again, I don't really like changing things like this because I don't remember what I did, right? I want to see every result in one table. And that's exactly what I do in here. So you do the polynomial in batch. Okay, I want to show you that every time I do this, you're going to run into the situation where you want to run multiple things, and it's always nice to set things up so that you can automate things and get the result in one table, in one Excel file. So try to design something like that. It's actually going to help you doing your research quicker. Okay, so let's do this. Okay, the first thing's the same, right? Loading all the data, all the libraries, right? But then here's the thing. Here's the difference, right? I wanna set it so that my parameter goes from 1 to 10. And I don't even want to hard code this. I want to generate all the parameters. So see how lazy I am. Like everything needs to be, I don't want repetition at all, right? But essentially, if I were to run, let me just run it here, okay? Okay, run, and run, okay? See, if I were to look at my parameter, it's actually a bunch of, it's a dictionary with a bunch of keys and value, right? So the first key is called 1, which is degree of 1, right? 2, degree of 2. I generate this one up to 10, 10th degree. So in this way, I can always, if I want to go to 20th degree, then I can just do that without changing anything. Like I can go as crazy as I want. So that's the beauty of when you construct something like this, right? So try to think about a ways to make sure you can change things in the future. I think that exercise will help you become a better programmer and like structure things better. Okay, I want to do 1 to 10. I think that's plenty, right? And the rest you can see that it's kind of the same because then I'm looping through the parameters, right? And then I'm constructing my, I guess this one not counting, but I'm constructing my x according to the value of the degrees, right? So my x will be changing, like number of x will changes every time I change my degrees. And then I just put everything into my polynomial, like linear regressions, right? And just run the whole thing, okay? As you can see that it's nice because everything kind of collecting into one big table. And you can see the difference. For example, you can see that my R square, if it's first degree, so that this is the linear regressions. It goes from 0.52, right? When I increase my degree, my R square actually increase. So which means that I'm actually capturing more trend, like more useful information in my model, right? But again, there's also a diminishing return, right? Once you go to a higher and higher degrees, then your R square kind of plateau, and actually getting worse once your degree become too high, right? So let's see what happened here, right? So first, my linear, just straight line, doesn't fit very well. Once you start to make parabola, yeah, it looks better, right? The cubic, it's even better, right? And then when you start to increase your degree, then you have more wiggles to capture, pretty much the noise, right? But once your degree become too large, then I think it's gonna go too crazy, right? This one maybe it shoots down too high, right? It starts to do strange things, right? And then I think that's kind of the lesson here. So do not try complicated model first. You always want to try the simple one first, because you don't want to go to experiment with this model. It's very hard to debug, and also it's generally more computationally expensive too, okay? And that is a lesson that I want to tell you, because it's the same thing when I see your like proposal, like not your, but generally, I always do, people want to do ANN, like artificial neural network, and I always advise against that one, because that one is too complicated. Like when you have something too complicated, you might end up with something like this that you cannot debug, right? Always try something simple, for example, linear polynomials, and as you can maybe see, support vector regressors. do random forest, do something like that first. Easy, fast to run, do that first. If it's not good, if it's not enough, do A and N, okay? But I mean, I guess in a way, if you want to publish, maybe you have to go for big model anyway, but always do the small model first so that you have some benchmarks. And then if you want to go crazy with the big model to publish, then you can do that. But once you have the good results, I think it's more fun to build, to do complex model when you already have the results, rather than you don't have anything, and the big models always fail. So that's kind of a lesson here too, okay? Okay, I think this is a good time to stop, but next, I think we can finish all the regression next time, and even we might have some time for time series. I think everyone probably gonna go through time series exercise in your career once if you go to data science. You cannot avoid time series, and it has some extra complication. So hopefully we can do that next time. All right, thank you. ขอบคุณครับ